Let's take a trip into infinity. You may think this would be difficult, but using the Mandelbrot fractal zoom, we can do exactly that.
The Mandelbrot fractal zoom is an image that shows more intricate details the closer you look at it. Let's see how this happens.
Let's start with the concept of complex numbers. So far, you've probably only encountered real numbers, such as integers like -1, 0, +1, and decimals like 0.25, 8.8, and more. These numbers belong to the real set of numbers, which can be shown in a real plane.
However, there are many math problems that can't be solved using real numbers, and this is why mathematicians introduced a complex set of numbers.
When you square real numbers, the product is always a positive value.
Let's look at the example of 1 and -1. When we square the value of 1, we get back 1, and square the value of -1, we also get a positive 1.
But consider the value of square root of -1. Here, the square of the square root of -1 would be a negative number, which would not be possible for real numbers. This is where complex numbers come into play.
The square root of -1 is now known as the imaginary number I, and when we square this value, we get back the value of -1.
A complex number, denoted by the letter z, is equal to x plus iy, where both x and y are real numbers which belong to the complex plane.
Instead of working with x and y axes, the complex plane is set up with real and imaginary axes. The value for x is the units of measurement on the real axis, while the value of y is the units of measurement on the imaginary axis.
If we have a complex number defined by z is equal to -2 plus 2i, to graph it on the complex plane, we must travel 2 units to the left on the real axis, and then 2 units up on the imaginary axis. Where we arrive, that is our point z.
By working in the complex plane, it allows us to explore a whole new realm of mathematics, including the Mandelbrot fractal zoom. To identify the Mandelbrot set, the equation Cn equals Cn minus 1 squared plus z is used. In this equation, z is our complex number, and c to the n minus 1 is the value of the previous index of the set.
But can we just pick any random set of numbers and zoom in? The answer is no. To be a part of the Mandelbrot set, the set of values Cn must produce a continual loop of the same values repeating over and over again. If this occurs, then we know that the complex value z is a part of the Mandelbrot set.
So, let's go back to our example of -2 plus 2i as our complex number. Using this, and plugging it into the Mandelbrot equation, we can see that for our n equals 0 set, we would have a value of 0. For our n equal 1, we would have 0 squared plus -2 plus 2i equals -2 plus 2i. So our value of C1 would be -2 plus 2i.
C2 being equal to -2 minus 6i, and C3 being equal to -34 plus 26i. As we can see, this does not produce a repetitive pattern, and therefore z is equal to -2 plus 2i is not in the Mandelbrot set.
Now, let's switch our complex number to z equals -1.
C0 will be equal to 0, C1 will be equal to -1, C2 will be equal to 0, C3 will be equal to -1, and C4 will be equal to 0.
Hold up, it seems that we have a loop here. If we continued collecting Cn values, we would continue to evaluate values of 0 and -1. As we have a repeated loop, it is clear that the value z equals -1 is part of the Mandelbrot set.
So now we have seen a complex point of z equals -1 that is part of the Mandelbrot set, and a complex point z is equal to -2 plus 2i that is not part of the Mandelbrot set. But what good does this do us?
Now, we can apply the Mandelbrot equation and evaluate over the full complex plane to identify which complex values satisfy the condition.
If we plot the complex values as different colors based on how fast the Cn terms increase, and plot the complex values which produce a loop as black, this produces the Mandelbrot image.
Let's take a closer look at the Mandelbrot image itself. Woohoo! Isn't that some pretty cool stuff? So as we mentioned before, the black portions represent the complex values in which satisfy the Mandelbrot set and perform a loop.
If we zoom in to take a closer look, we can see that the edges of the Mandelbrot set are different. Looking at this edge, we see that 5-fold symmetry is produced, relating to 5 complex points which are a part of the Mandelbrot set.
And as we move down the image, we can notice that next to it, there's a 7-fold symmetry, and then there's 9, and then 11. So now, let's go way further down the edge and see what's there.
As we know, the symmetry will continue to increase. We see that the edge starts to curve in on itself and employs a super cool and intricate structure.
Now, if we take a step back and consider the system as a whole again, we can find an almost exact replica of the system, just in a smaller form.
There exist a multitude of various algorithms for plotting the Mandelbrot set. The only limitations on the set are the computer itself. The set will continue to zoom and produce beautiful structures and visuals until the computer running the algorithm hits its limit.
Just like many beautiful structures in our world, no one designed these intricate features.
They are simply embedded into reality around us.